We mentioned backstepping system, right? The design procedure, for example, in this system, we have two subsystems. Okay, system 2. That takes the input as U, generate to be exact, use y dot, and that becomes the input of the second system, that is system 2. That come out with x dot, and do the integration, you got x. Okay, so basically this is subsystem 2, this is 1. Right. So we say this is 1. This is one system. This is one system. Okay. The output of this becomes the input of this. And here's the regulation problem. That means the objective 1 is for x converge to 0. Okay. And for that objective to be achieved, you require that this y to be designed as some signal, right? You can consider y as a controller, virtual controller, right? Because this is a physical controller. So you consider y as a virtual controller, and y had to be, for that objective to be satisfied, y had to be some specific signal, right? And we say the objective here, which is the control objective of this subsystem, is for y to track some YD signal, right? Okay, because when y can be random signal, but for x converge to 0, y cannot be random, right? Y had to be converged to YD, okay? And y is controlled by this control input U based on this dynamics, okay? So that means you have two systems, two controllers to be designed for two different systems, okay? But in fact, you have only one physical control input, that's U, okay? So is that clear that why in the design procedure we introduce YD, although it might not physically exist, it's just a desired signal, right? We mentioned from last time, we mentioned YD as a desired signal here, right? YD is here. YD is the desired signal, okay, which is designed based on the demand of the first system, right? Because the objective of the first system is x converge to 0, and that requires a virtual control signal to be YD, right? So they totally designed from the first system, okay? But for the first system, the y, the output of the first system, which is y, might not be YD, right? Because you can consider that you want to design a controller that track for the output y to track a desired trajectory. That's why we say it's YD. YD is the signal, okay? It's designed from the first system and the desired signal for this y. And the second system is responsible to design a controller that enable y to track YD. Okay, so the objective for the second system is to enable eta is 0. Okay. So that y can track the yd, which is designed from the first system. And that's the connection, that's the bridge between first and second system, the yd signal. For the first system, yd is a desired signal, is the virtual control. For the second system, yd is the reference signal that the second system have to be controlled to track that tracking signal. Okay, 这个 controller 吗? It's from the analysis. This is controller, right? And for the first system, the controller is designed. It's clear that this controller is designed from this ODE, right? It's easier to see that. But the second one is not that obvious, and you have to get that insight from the stability analysis. Okay, so usually, what I did was you choose a de novo function, and you put the signals that will be 0, right? According to the objective, the signals in here have to be 0 eventually. Okay, and so this is for regulation. This is for tracking of the second system. And v dot is x dot. Okay, and you substitute the dynamics. So the closed loop dynamics of the first system is that number 3, that k1x plus gx eta. And eta dot is the closed loop system of the second system. Okay, so that's y dot minus yd dot. Okay, and the control access is through y dot. Okay, because y dot is u to that. Is u. Okay. So here's the design process, and eventually you know what you need is ND, right? And that is something like this. Okay. So here you need to design control U to bridge the gap between this and this. Okay. So here it gives you minus k1x squared plus x gx eta plus eta y dot, which is u, minus yd dots. Okay. So this is exactly what we want to achieve for the first system, right? Okay. And this, we need to cancel out this. Okay. And how can you cancel out this? We can design, we can cook around the controller, right? So you can design U as, first you need the feedback term, so you will do, here's K1, here's K2. You will design U as minus K2 eta, right? Then you need to cancel out this term, right? You have eta here, so you need to put x gx in U. So this minus x gx. Okay. And finally, this term had to be gone, right? So you design yd dot here. And everything is known. This is measurable, known, right? And that enable and designing this U give you that guarantee that beta will be negative definitely. That's how I design it. Okay. In the robot manipulator, there are more terms that characterize the physical behaviors. So M is the mass of the robot manipulator. Vm is the coriolis effect, okay, which is a function of Q and Q dot. F is the friction, okay. G is the gravity, okay. So this ODE truly represent or truly describe the robot manipulator dynamics, okay. And in here we assume that all these these parameters are known. That means M, Vm, F, and G are all known constants. Well, here the difference here is M is a function of Q, okay. And before we assume M is a constant. Now it's a function of Q because if you have two joint robots, for two joint robots, the inertia, which is same as M here, depends on the angle, right? Because compare with this configuration and this configuration. Okay. For this configuration, the inertia will be is larger than this one, right? It requires more torque in here, in this motor, in this joint, compared to this joint to keep at this pose, right? Okay. Because of the center of gravity of this joint is here, and this is here, this is here, this is here. It's much away from the heat, right? Okay, so the inertia here is much larger than this. So inertia, or the M term here, is a function of Q. In other words, it depends on what the pose of the robot manipulator is. Okay, so it no longer be a constant. It's a variable now. Okay, so it's tricky when you take the time derivative on your above function. It won't be a constant. Okay, you need to consider the time derivative of M. Okay, so that's a bit tricky here, but that's fine. And Q and Q dot are measurable signals. You can be measured. Okay. And now, so this part is dynamics. Now it's kinematics. Anyone knows what's the difference between dynamics and kinematics? 有人知道吗? What's the difference? What is the difference between the two? So you will see M, the inertia or mass, in dynamics, but they won't appear in kinematics because kinematics is about the motion. Okay, it's not about the force or the momentum. Okay, it's all about motion. So in other words, the J, which is Jacobian matrix, it transfers the Q dot to X dot, and Q dot is in joint space. X dot is in task space. Okay, so task space. So here is the end effector. Okay, you can put the end effector can be used to pick up some payload or do whatever you want it to do. So the position of this end effector matters. And usually we design in text space, which means we describe the position of the end effector in the text space coordinate, which is x, y, z. Okay, but for joint space, that means that x, y, z, or sometimes theta x, theta y, theta z. The orientation of the end effector, and this is position of end effector. And so I cannot use theta. I use Q, Q1, Q2, Q3. But for people who design the controller, it's in joint space, right? Because what physically you can control for each joint is the torque, right? So this is in text space. This is in joint space. Okay, 听懂吗? Like if you want this endpoint, this end effector to follow some trajectory, okay, to assemble the cars in the factory, okay, you need to put some glass, okay, this stuff from here to here. You will describe these trajectories in the text space, right? The trajectory will be represented. You have waypoints here, and you will describe those waypoints in the text space, which is, you know, what x, what y, what z, this point is, right? That makes more sense for people, for the operators today. But for robots, usually what you control is the joint. So that's in joint space. What's the angle of this joint, and this joint? Okay. So in that dynamics, in this dynamics is in joint space, right? You design the controller is torque to a system that control the joint. Okay, that control the angle of each joint. But in reality, your desired trajectory is given in a test space x, xd, and these two systems consist of a backstepping. These two systems consist of become a larger system that require the backstepping technique, right? Because for the first system, the control input is so eventually the objective will be, for example, for an effector to be held at the constant position in the space, right? For example, the origin. So the objective is for x converge to 0. Okay, for the end effector, to be at the origin. Okay, and that's x. So to deliver this objective, we need to design torque as to control the Q's such that this x can be in 0. In other words, the objective is designed for this first system, but the control input is in the second system. So we consider this is a system 1, this is system 2. Okay? Okay. So system 1 that generate x star or x, whatever, right? And the input of system 1 is the output of system 2. Okay. And And system 2, the input is torque, output is Q. Okay, right? 这样对吧？ And objective is here we just consider regulation, or if you want to do tracking, we can do this. Okay. And the XD will be the desired trajectories that describe how you move the pedal from here to here. Okay. Come on. The trajectory is XD. It's a function of time. Okay, so now we need to design the backstepping controller for this dynamics, for those two subsystems. Before we get into the controller design, we need to make some assumptions and properties. So for simplicity, we assume that we have exact model knowledge and the desired trajectory of the joint and its velocity are measurable. Okay. And J inverse exists and is bounded. It cannot be zero, otherwise it will require infinite large force to be applied on the torque. Okay. And you will see why in the formulation, okay, in the seconds. And the property here is the skew symmetric. And here you can see that in the bracket you have m dot, right? Because as we mentioned, m is a function of q. In other words, it's a function of time if q is not constant, right? So to cancel out m dots, we can use these properties, okay? So this is called skew symmetric properties, and this is a useful property for any robot manipulator systems, okay? So for the first system, the block diagram is this, okay? You basically just convert from Q dot to X dot, okay? Or X here. You convert from joint space to text space, and you have some feedback term here, okay? And adjective is a regulation problem. So as we say, in the first subsystem, you had to design the virtual control, right? And just by observation from the dynamic system, we can design the virtual control as this. Okay? Virtual control as this. Any question? Just a feedback because there's a regulation problem, right? This QD dot is the desired signal for this Q dot. Any questions? So here's input is Q, right? Input is Q dot, right? And Q dot is the output of the second system. But because Q dot for X converge to 0 require a design of a Q dot signal. And that signal is QD dot, right? But Q dot, but unfortunately, Q dot might not always be QD dot because it can be initially located anywhere, right? So there's a mismatch between Q dot and QD dot. Okay, so the way to match the difference is design the controller on the second system. Let's drive this Q dot to be QD dot. Okay, so for the first system, that's all you need to do. Design the QD dot, the desired signal for this system. Okay. And here is the second system, right? It gives torque as an input and output a Q dot. Okay. And the objective for the second system here is enable the Q dot to track the desired trajectory such that the objective one can be guaranteed. Okay. So usually in the controller here, the physical control that will consist of feedback terms, cross terms, and nonlinear terms. Okay, so for the first system, the way we design controller is you can add and subtract the desired trajectory x d dot. Okay, and you combine the mismatch between the two and that can be defined as eta. Okay, so eta is defined as the tracking error for the first system. Okay, and when the tracking error is 0, that means that your x dot is equal to x d dot. Okay, and x d dot is just a feedback control. Remember, right? Because x d dot is just a feedback control. That means that if this eta is 0, the closed loop system is a first order feedback system, linear first order stable system. The second system, right? This is the objective for this second system. And if eta is 0, eta is the mismatch between Q and QD. If this is 0, from that dynamics, okay, J eta plus J d dot. If this is 0, the closed loop dynamic becomes this. And what's that? You design this is by design, and you design as J inverse Kx minus. Right? So that means it's minus Kx. So x dot equal to minus Kx. That means it's a globally exponentially stable, right? Which implies x will converge to 0. Okay? So all this cannot be achieved without designing this guy, without designing this. Okay? And that's the virtual control of the first system. So all you need to do is design torque tau such that you can enable this Q signal to track this. Okay, that's the job for the second system. For the second system, so that's the closed loop for the first system, and you can see that eta is 0 is become a linearly first order differential equation, and it is exponentially stable. And for the second system, objective is QD track QD dot. Okay, and that's where in NQ double dot, here's the access for the control torque here, right? And all these terms, because it's from the open loop dynamics, so you need to find a way to design torque to cancel out this, okay, and this. And some terms could be cross term, okay? So eventually we design this controller as this big stuff, several 6 terms, okay? And again, that's designed from stability analysis. Okay, there's no way for anyone to just by observation design the controller first and do an analysis later. There's no way, okay? Everything is reversed, but for teaching purpose, I need to do this. I need to first give you the torque, the control input, okay? So the closed loop system becomes this, okay? So next, you can substitute the 2 closed loop systems into readable function and to do the analysis. And the cross term will be canceled out. Nonlinear terms can be canceled out, and you can get a negative definite system. That shows both signals x and eta will converge to 0 asymptotically with asymptotic tracking. Okay? 听懂吗? Okay. So this means that eta will eventually be 0. Eta will be eventually 0. And that means that Q will track QD. And as long as Q becomes QD, X will be 0. Okay. So I will start from here next time. Okay. See how to teach you how you design this torque, which looks very scary, but in fact it's fine. And you need to remember that every term here is known, right? VM is known, QD is known, GF is known, and all these have to be known. Okay, and this J inverse is the inverse of Jacobian matrix. And imagine that if you are considering a 6-axis robot arm, this J matrix will be a 6 by 6 matrix, which is a bit large. Okay, but it's fine. So, and remember that I say J inverse cannot be has to be exist, because if J inverse doesn't exist, or J inverse is or J is if J is 0, okay, if J is before a few slides back we say J inverse has to exist. Okay. In other words, J cannot be 0, because if J is 0, the inverse will be infinity, and they require your torque to be infinity, right? So J inverse has to exist. Okay, so J cannot be 0. In other words, J cannot be singular.